All right, let's go ahead and continue. Today we're going to go through more about caches. It's going to be a quick review of associativity, and then we're going to go into cache coherence protocols, which is the meat of this presentation today. So I know a midterm's coming up, and I have it scheduled on the syllabus. As I talk to people in here, they seem like it'd be okay if I made a midterm be a project similar to, project 1, project 2. It's going to be a little different. I'll have you working with, excuse me, working with a full system simulator that actually simulates everything, and it's an open source one out there. And I'll probably have you basically running different multi-process benchmarks and show me that you can actually mess with the cache system to add a couple of features and then get some different results back. So it'll be a little bit more researchy, which I think will be a lot more applicable to this class, unless you really all want a midterm.
Death to midterms.
Yeah, that's usually what I get. So I don't like giving them, so we'll avoid them this time. But I'll make sure I get that written up for next week, and you'll probably have a good 3 weeks to get that turned in. Okay, so associativity and caches. This should be just a kind of a review of last time. So real quick, why is caching important? Everyone except Matt.
It makes things quicker.
Makes things quicker. What in particular does it make quicker?
Makes registry calls, or in
Not registry calls.
Memory calls.
Memory calls quicker. Yeah, because called memory. Yeah, it could take what was it, 200 to 500 clock cycles just to get back from main memory. While if it's in your L1 cache, it usually takes between 2 to 5. So, which is significantly faster. That's a factor of 100. Speed up right there. But as we went through last time, caches had a lot of issues you had to take care of. Namely, in order to capture in order to ensure that all the data was inside the cache, you had to take care of spatial locality and temporal locality, because a cache can only represent a part of memory. So here we're going to talk a little bit more about associativity. And okay, sure. If we call a direct map cache, which is not fully associative, you can think of this as a one-way associative map. That means each line in the cache line can only map directly to certain parts of memory. So for example, here you have orange can only go to those orange lines, blue can only go to blue lines, yellow can only go to yellow, and green can only go to green. Cool. So, do we get to do examples? Let's go do an example. So if I were to read, I feel like they're after us or something.
It's the Shem police.
It's the Shim police. All right, so writing up on the board, so sorry people online. 0x, what do we got? We'll do 0, 0, 1, 1, 1. What would happen? So we're getting a read from here. First off, is it a cache hit? No, it's a miss. So it's a miss. Where is this in memory?
110.
So which line from the top?
Oh, okay.
So this is the first line. Is it that one?
No.
No.
That.
Yeah, this one. So it's the fourth line from the top. So where does that go? In our cache, our 4-line cache.
I guess the screen is going to go.
Okay, it's going to go to the grid. All right. So let's see. We got this valve becomes 1. Dirty. Is it dirty when it's first read? No, because we're reading it. The tag. Sorry, it's the first 2. So that's the 0, 0. And then we have the line index. Line index, and then of course the block offset. So when we put the 2 values here, 1, 2, 3, and 44. So line index 0, 1. This is line 0, 0, line 0, 1. Try that again. 0, 1, line 1, 0, and line 1, 1. There's a line index right there, and there's your tag, and there's your block offset. So line index is 1, 1, so it's going to go to this line. Your tag is 0, 0, so you put the tag in, and then the block offset's 1, so it's going to be right here, it's the 44. Y'all see how that happened? Sorry, people online, I have no way to show you this. Okay? Are we good so far? Yeah, okay.
I'm with you.
All right, so let's go ahead and write to it. We'll write the value 256. So is that a cache hit or miss? Well, first check the line index, 1111. So it's this line. Do we have that tag in the line index?
Yeah.
Yeah. So it's a hit, and we're changing the 123 to a
256.
256. All right. What else do we have to change?
Dirty.
Dirty, right. So this is a write back, because when you have write back, you have dirty bits. So there we go. And then we'll go down here. We'll do a read. Let's go from 0, x. Oh, let's do 1, 0, 1, 1, 1. All right. So line index 111 right here. Here's the tag. Is that a hit or a miss?
What is the tag?
The tag is 10.
You miss.
Miss.
Miss. So what's going to happen?
It's going to blow up.
It's going to blow up. Good try.
Do I have to read it from the memory?
We first have to evict the cache line, because we have to first write this back, because it's dirty.
But it's not going to the same one?
No, this one goes over here.
Yeah.
We're trying to read from.
We're writing back as soon as another thing gets wrote to the
It's
cache?
another
Well, hold on.
green.
Let's go and step back.
Oh,
So-
it is another green one?
Yeah. So we rewrote. We're trying to read from 10111, which is what?
Oh, I
This
was
guy
looking
right
at
here.
the 0, 0.
Oh, okay. Right here. Right. So we have to go this. We have to evict a line. We have to evict this line. He's dirty, so we need to write him back. So we'll go ahead and write his values back here, 256 and 44, and then we can read in the other values. 10, and then of course, what was it, 28? Yeah, 28, 192, 12. All right. So what was the problem here, or why is this not desirable?
Because you've got three.
We got 3 open
available
spots,
spaces
but
and you're kicking out.
they're kicking out the one that we're using. All right, we could have easily used this cache more efficiently. Okay. So two-way set associative. You have 2 of them. So all the orange ones can go. The orange has 2 lines to select from, hence two-way. And down here you have 3. I'm going to skip a bit here because the block offset isn't unchanged because your block is still just 2 blocks, so you just have 1 bit there. Now you only have a 1-bit set index because you really only have 2 blocks here. You have the 0 and the 1. And you have a larger tag, so your tag would be 3 bits. So this is luckily here, when you pull in a cache line, or pull in something from main memory, you at least have 2 lines that you can write to. So that's going to do a little better job of utilizing your entire cache.
So what is the trade-off?
For this versus that. So the big trade-off is here. When you, architecturally speaking, when you're designing the processor, it takes less time to look up the cache because you only go to 1 line in the cache, you immediately check the tag and you're done. Here, if you need to figure out if you have a cache hit, you have to go to multiple lines, do a comparison in parallel, and then come back and fix it up afterwards. That is slower to do. It is slower to do that two-way than a direct map. But on the flip side, if you're able to utilize your cache better, because remember, memory is the bottleneck, then the slower cache may actually be more useful for your application. And how do we figure out which one is the best?
Simulate it.
There you go. There's keywords here. One of them is
Exempt from the midterm.
you simulate the when we don't have any intuition about what's going on, you just simulate it to try and figure out what the answer is. We run a bunch of benchmarks and we find out which one for our particular processor is better. By the way, some processors, direct map's going to be better. Others, two-way, four-way, or even eight-way is going to be more efficient. All right. Let me roll back because I didn't go over what was down here. Compulsory miss is the first reference to a memory block, so that's what happened first when you try to read something in. How do you reduce your compulsory miss rate?
Add more entries
To the
just in general.
It's not
the
making
first
your
thing-
cache bigger necessarily. It's increasing what?
Oh, the block size.
Yeah, so you increase the
whatever
number
it's
of
called.
blocks you can have, because that'll take advantage of spatial locality, where when you reference one memory address, you're probably going to reference the stuff around it. So if you want to lower your compulsory miss rate, you increase your block size. What's the capacity miss? The working set doesn't fit in your cache.
Make the cache bigger.
Yeah, you just make the cache bigger. Unfortunately, that's about it. Or increase the associativity if you have a direct map or two-way associative. Or actually, I'm sorry. That's the answer to the conflict miss. Sorry. The conflict miss is working set maps to the same cache line. That's to fix that one. That's where you increase your associativity, or you become fully associative. Because that's the error here is when we had everything go to the same cache line. That's conflict miss because you had other lines available. So those are the three C's of cache misses, or the three problems right now at least. We're going to introduce a fourth one later on.
Is that also a C?
Yes, it'll become the 4 C's. So rule of thumb, increasing associativity decreases your conflicts, which is great. A two-way associative cache has about the same hit rate as a direct map cache, twice the size. And that hopefully makes some sense, because if you have twice the size of the direct map, then you're hopefully splitting up your memory a little better. Okay. What do we have? Vexifarian cache parameters, total cache size is your block size, times your number of sets, times your associativity. Okay, it should decrease. All right, ignore this slide. Okay, actually, that part's really helpful. Block size, to think of this pictorially, is how long your cache line is. If you were back here, remember that your block size is the number of data blocks you're storing. Your sets is how many, different colors. Yeah, you can think of that, different colors or different ways you're mapping out there. And the associativity is how many lines you can address for each color or each block you have out in memory. So, the point of this slide is that increasing associativity, aka adding more cache lines over here per color, should decrease your miss rate because you have more items that you can select to, but increases your hit time because it takes longer to do a tag lookup, and also you have increased area requirements of your cache because you actually have to map out all the gates in order to do that comparison in parallel. So this is a trade-off, and like I said, we basically run a bunch of numbers and figure out which one's the best. All right, block size, looks like we're going to each one of it. Positive, exploits spatial locality, so it reduces the compulsory miss. It also reduces the tag overhead, because your tag is just looking at those bits and then you jump a certain number of offsets. So that's actually a pretty big bonus right there. Reduce transfer overhead, and the reason for that is most memory nowadays has a burst mode where they can ship you a big chunk of memory, but it still takes the same amount of time as just a small amount of memory as well. So having a big block size means you can capture all that coming from RAM. Negative, fewer blocks for a given size. What that means is that if you had huge cache lines, then you may have some more conflict misses with your associativity. Increase the miss transfer time. The reason for that is when you miss, you got to write it back out to memory. And if it goes beyond that burst cycle, you're going to be slowing down the machine because you got to do multiple cycles of writing it back to main memory. And you also wasted bandwidth, because if you were just using this part of it, then the bandwidth for that and that are essentially wasted because you didn't need it. So I'm going to say this again. How do we figure out the block size?
Throw paint at a wall and see what sticks.
I like that.
Simulate it.
Assimilate it? Okay. Just making sure. So increasing the associativity, aka reducing the number of colors, I guess is the way to think of pictorially. But really it's allowing each memory line to map to more than one cache line, the number of cache lines it can map to. Reduces your conflict misses because now there's multiple lines that you can map to, so increasing it, that's the positive of it. Low associative cache can have pathological varied. Well, that's an odd way of writing it. Basically, if you have low associative, you can have a very high miss rate, like we're talking about with the direct map cache. You might be just operating off one cache line when you shouldn't. You should be able to map to other three. Unfortunately, when you become higher, more associative, it increases your hit time again, more hardware, and decreased improvements past 4 or 8 way. Yeah, after about 8 way, there's really no one's shown any significant advantage there. Okay, so replacement strategy, we touched base on this. If you have multiple cache lines and one of them needs to be evicted, how do you determine which one? LRU, which is the least recently used, you can find the one that was last used the furthest back, is the intuitive one, but unfortunately it's very difficult to implement with high associativity, and it actually has the worst performance because it's an n+1 element array lookup, because you have to search basically every single array or element in there, so that ends up not being a good thing to do in hardware, and hardware and O of N operation is way too slow. So you could do random, it's easy to implement, it's performance, and easy to implement. You just pick one randomly, just flip around which one you're evicting. Hey, they do that. Some people do it. It's actually not that bad. They found out that if you have high associativity, the random replacement actually is pretty close to LRU. So as long as you have a highly associative cache, random is actually a pretty good algorithm to put in there. Optimal, replace the block that has its next reference furthest in the future. All right, how are we gonna do that?
Time machine.
Time machine. We'll all have little DeLoreans running around and going. Yeah, it's just not practical.
Okay.
Yeah.
I thought it was a real thing.
No.
I was like, wow, they've come a long way with hardware.
Hard to implement, aka it's not gonna happen. That'd be great, be able to predict the future. Of course, we do that somewhat with branch prediction, but this is going to be even harder to predict. All right, a couple other cache designs just to get a good refresh of what's going on. Write policy. How do you deal with misses? And the point of that is if your cache is someone decides to write to memory, but it's not in the cache. What do? You can do write through, which writes it out to main memory and no allocated, or you can do what's the other one? Write back and write allocate. Okay. Yep. So write through, you write straight to main memory, you don't allocate it. The other one is write back, where you write allocated. So what's the benefit of the top over the bottom?
The tops will be faster
In what situation?
when you're writing. Well, if there's a conflict, then you don't have to worry about writing to
So
the
if you
cache first.
if you're just writing to some variable that you're never going to read from, then write through is possibly going to be faster because you're never going to have to evict a cache line because you're never going to read it. Very common for L1 caches to the L2 because the connection between these caches is very fast. So it's very common for L1 to be right through to the L2. And do you know what I'm talking about, L1, L2?
L3.
And then there's L3. Yeah, okay, good. Yeah, the caches of the core. So
Level 1, level 2, level 3.
yeah, hey, some people not talk too much. How about write back? When would write back be advantageous?
When you're actually modifying the memory.
Yeah, modifying the memory a lot, and because you're going to delay when you actually commit that to main memory until you have to evict the cache line. which means your reads and writes are going to stay within that very fast, high-speed bus between your CPU and your cache. Ends up being very common for L2 because the connection between L1 and L2 is plenty fast. So L2 will be the write back. It's the one that kind of starts buffering communication up to your L3 or to your main memory. See, write validate, write allocate without fetch on the write. Okay, so this one, instead of writing it straight to main memory, you put it into your cache, and then you basically mark it as dirty without actually going out to main memory and reading anything. The only issue with this is you have to mark that all your other elements in your cache line are not valid. Do you understand what I mean by that?
Sure.
No? That sounded like a no. So, if I decide to, and then this map to some piece of memory, dot, 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 you know, right here, dot, 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 out in main memory, right? Here's your cache line. It goes out there, and we're going to write 32 to this block right here, right? So 32 would be get right here, but it's not going to write anything yet. It's not going to interact with main memory. Are these elements right here valid? No. No, because we didn't get them from main memory, so we don't know what those are. So we have to somehow mark these three guys as invalid for the time being until we either write to them or read from main memory. So this is actually very confusing.
Is that because they're empty, or?
Well, no, they're not empty. We just haven't read from main memory yet, so we don't know. We have to mark that we're not storing the correct values. We're storing the correct value here because we just wrote to it, but we don't know about these three values because we haven't done anything. Haven't read them from main memory. We're just reading and writing memory, guys.
That got deep. That got deep.
That got deep. All right, buffering. All right, you delay your writes until bandwidth available. This is more of a, if you have a cache right here, a line gets evicted to main memory, you might have a buffer in between it that buffs, that this actually gets written to first, and then once it fills up, it bursts it out to main memory. That's just so you're not using the main memory bus too much. It's like a buffer cache. It's a cache for the cache. Write back buffer, similar as well. Okay. Ooh, a victim cache. So, this is definitely this is probably one of the more extreme things I've seen. So you're going to have your regular cache, direct map, and then you're going to have an extra cache that's fully associative. That's your victim cache. The idea is that your victim cache, while smaller than the regular cache, is going to hold the most commonly used cache lines for your entire cache. So you're literally caching the cache.
It's caches all the way down.
It's caches all the way down. Let's see, do we do an example here? So if we find out that one's been used, we put them up here in this victim cache. And then, wait, what's going on here? And then when he changes, it's not going to say anything. Okay, great. That would also be added to the victim cache because he's fully associative, so he could go up here as well, and it would just store the more hotly used items. Let's see what we got. Not very useful for associative caches. I said this extreme because it's not used too much. A hash rehash cache. Are we going to have this? Okay. So normally, we would look up the tag and then continue on. But in a hash rehash with a miss, we're going to, let's see. Did it show me how this works? Hold on a second. It is direct map. Notice that the line, let's see, we've got 2 blocks here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That should be 16. So 4 bits are going to be which cache line it is. So notice that these are 1, 0, 0, 4. So that's 8 plus 9. So everything is going to go to the 9th cache line. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm off by 1. Oh, because 0 would be up here. So they all go down here because they're on the same set. So they would all go to the same cache line, which would mean the next reference here would normally be a miss, and you'd want to allocate, you'd evict that line and allocate somewhere else. You would normally evict this line and then move the new line in there, but in the hash rehash cache, you're actually going to move the old one up there, and then,
Spiffy.
and then that way, if you have a further miss, you know to jump up there anyway. So there's an extra rehash algorithm inside of it to take care of, to try and use different parts of the cache. When have you seen this before? Yeah, it's a hash map inside of hardware. All right, so what would be the advantage of this one?
You can use up other entries that might otherwise be empty.
Right, so if you're in a direct map cache, you can use other entries inside of it. All right. Oh, you got to mark that, yep, as it's somewhere else now.
Is the R for rehash?
Yep, rehash. So the problem with this one is calculating performance. Your primary hit time isn't just a normal direct map, but your rehash hit time is a sequential tag lookup. You got block swap. Ends up being comparable to a two-way associative cache. Sometimes it's better, sometimes two-way is better. How do we figure out which one's better?
Paint at the wall.
Simulate it. Paint at the wall. Okay. Compiler support for caching. Ooh, I don't know if we have time for this.
Is it the thingy thing with the thingy thing and the thingy thing and the, you know what I'm saying? With the row versus column access?
So has anyone showed you the blocking? How if you do matrix multiply one way, it's
Yeah,
slow.
that thing.
Yeah, and then
Yeah.
you did in undergrad.
Yeah.
But if you just rewrite your code a certain way, it does the same exact operations, it'll actually have a significant speed up.
Yeah.
No time of block. Okay. Note to self: I will need to do that for next class.
Or
But-
you could just play your old video.
Play my old video right now. I could try and find that out. Yeah, that might work. I'll videotape my computer. Record my computer playing the YouTube video of the other one. Okay. So compiler support for caching. You have an array of structs versus two arrays. All right. What's going on here? What would the compiler want to do now that it knows you're using a cache?
Utilize the cache.
Utilize the cache better. How would it do that?
By doing compiler magic.
True. So if you were looking at the nitty-gritty of your program and you wanted to utilize the fact that these machines have a cache, how would you want your memory stored?
It blocks the size of the cache.
Okay, yeah, you want them in cache, yeah. Basically aligned to the cache. That's correct. You want them aligned with the cache. So you want the data to enter the size of the whole cache line. Yep, that's a good one. What else?
Sequentially? Like,
Yes, you
yeah.
want them to be sequentially. Why would you want it to be sequential?
So you don't have to jump all over the place and have a bunch of loads.
Right, because if you notice in a direct map cache, it's the mapping is jumping from one to another. So if you have a direct map cache or a low associative cache, which you usually do, if you put all your memory sequential, then you'll be utilizing the entire cache a lot better. So that's why array of structs versus two arrays. Oh yes, row or versus column. If you were doing column, then you're going, you know how you go through the column of your array? If you go through the columns, you're going to be going each element inside the cache. But if you're going by the row, like here, you're actually going to go to another cache line, to another cache line, to another cache line, which will be significantly slower because you're trying to pull in multiple cache lines and probably evicting old ones. While by column, you're actually going through the entire cache. What we got? Place, data placement, pack working set to same cache line, map non-conflicting addresses as possible, right? See if I can give you a good example of that next class. All right. But you kind of understand what's going on here? This is actually a huge topic for architecture.
What's better for the array merging with structs or two arrays?
That depends. Because if you're going to use all the elements of the struct, then you want an array of structs. Because otherwise your two arrays, you might have one right here and one all the way down here, you'd be jumping back and forth.
But if
So-
you're not going to use it all.
If you're not going to use it all, then it may not even matter that much, because who knows what you're getting in there, and then maybe you can align that second array so that it would be in a different part of the cache. But row versus column depends on how you've set up rows and columns. And then alignment, because you want to make sure everything's within the cache block. All right, prefetching. Well, in general, this is already done if you think about it. Once you get one piece of data, because in general you may be only reading 1 to 4 bytes, but when you have a large cache block, you're already prefetching some number of elements after it, right? By reading in the entire cache line. So that's a way of prefetching. Bless you. You could also, in hardware, once you fetch one cache line and you start reading it, you can also read the next cache line as well, and that could potentially give you some extra hits. You could also have a software prefetch. Our machines do have an instruction where you can prefetch a line if you know you're going to use it soon. That way it will be in the cache. And then you can do other types of prefetching for different caches. It turns out in hardware, it's useful for the L2 because your L2 is usually fairly large. It's not useful for L1 because it's so small and usually very low associativity. It's very problematic for an L1. L2 though, it's pretty good. Ooh, what's this?
Pretty.
It's pretty. All right, does a cache miss reduce performance? So we've got on the right. Instructions per cycle with respect to an ideal memory system. All right. There's a percentage, so you want to have 100%. And no one is telling me what these colors are. All right. I believe it's a lot of lines. All this graph is telling me is once you start having memory problems, your performance just falls drastically. I think that graph needs to be fixed. We're going to go on. Oh, that's it for today. I mean, it for this, sorry, not for today. Good
Too
try.
late. You're on record.
Oh, man.